Picastro. It's like Instagram for space nerds. Well, good evening. Welcome to Space Oddities. We hope you're well. And tonight we've got usual suspects. Well, we've got Roger, although he's invisible at the moment, but he's got some technical problems. We're working around those. And so how are you, Daz, first of all?
Lovely, jubbly. Thank you very much. I was just telling everybody that my little Sea Star family has grown. The S30 arrived today. So I got the baby. So we're just waiting for the daddy.
Yeah, indeed. And how's Lou today?
Oh, doing well. Actually had a clear night last night, of all things. So did a little observing.
Yes. Oh, fantastic.
Real surprise. In 95 degree weather. Well, let's see.
Is it 95? God.
Fahrenheit. So wait. Kelvin. Let's see.
Wait. So we know what 95 Fahrenheit is. I mean, you have to remember, for us slightly more older, more mature people, when we were young, it was Fahrenheit. It only really changed to Celsius.
Okay.
About what, 30 years ago, 40 years ago, maybe. We grew up with Fahrenheit, so we know exactly what.
Yeah, with Fahrenheit also we had pounds, shillings, and pence.
Oh, luxury.
You know, groats for those old enough.
Anyway, welcome to Space Oddities. Thank you for being with us on this Tuesday evening. If you're new to Space Oddities, you're especially welcome. Why don't you introduce yourself in the chat? Just say hi. That's all you need to do. And let's see who we've got. If there's anybody around. Derek, hello. Ian, welcome. Stuart, nice to see you virtually. Kev's here. Hi, Kev. And a few others. So you're all most welcome. Thanks for being with us tonight. We've got quite a few things for you tonight. The main event, if you like, Daz is going to be talking to us, asking the question, how can we predict really damaging solar events, the sort of events that might destroy our civilization, like the famous Carrington Event of the 19th century. So we're going to be having a look at that. Lou's got another battle of the bots. What have you got for us tonight, Lou?
Battle of the exobots. Looking for exo worlds.
Fantastic. Roger's still looking confused, so we'll just hope that he that he can sort his sound.
Can we hear you, Rog? Can you speak?
Yeah, we can't hear you, but
can hear you.
Yeah. So there. Also,
good job. We probably can then.
Yeah. Also tonight, I'm going to be doing part 2 of the Square Kilometre Array. You may remember we started that last week, and tonight I'm going to be looking at the precursor and the pathfinder telescopes of the Square Kilometre Array. What the hell are those? Well, stay tuned and you will find out. Obviously, we've got our regular features. We've got Constellation of the Week, we've got Einstein of the Week, and the usual Night Sky Guide, gallery, and news, and all sorts of other stuff. So thank you so much for being with us. We hope you're all well. I think what we'll do, first of all, just do the normal housekeeping things. Don't forget, if you would like to support Space Oddities, you can do so in a bewildering number of ways now. You can, first of all, buy us a coffee, and you can click the link that is shortly going to appear in the chat, or you can scan the QR code here. That will take you to our Buy Me a Coffee or Buy Us a Coffee page, where you can make a donation for a cup of coffee. A big thank you to Stuart, who donated, who gave us a coffee each a few days ago. That was very generous of you, Stuart. Much appreciated. And as always, all of the money goes towards keeping Space Oddities on the air, as it were. You can also, of course, visit the Space Oddities shop, where you can buy your Space Oddities merchandise. And we've got T-shirts and hoodies on sale in the Space Oddities shop. And again, you can scan the QR code there, or you can click the link that should have just appeared in the chat. So, you know, we're midway through summer now. You should really be thinking about the autumn and temperatures dropping, and getting your Oh, just by the C star. Yeah, the C star 70, presumably the new one.
Right.
Yeah, you should be thinking about getting your Space Odysseys hoodies ready for the autumn when the temperatures drop. So that's the Space Odysseys shop, and you'll see everything there. And thank you very much indeed. Let's just get rid of that, and I think we'll move on. Just before we do, though, just a reminder that you can also donate directly to us by clicking the $ icon underneath the chat window to make a donation directly. No matter how big, you're quite welcome. And you can also, of course, join our Patreon. Our Patreon you will find at patreon.com/Space Oddities, and join the community there. You get all sorts of benefits. You get the Space Odysseys presentations that we give you every Tuesday. You also get a lot of Space Odysseys videos. For example, all of our Moon Month videos, nearly 50 of them, are there. You can download them and keep them and show all your friends, of course, if you want to lose them. And for just £5.50 a month, pounds, that is, plus VAT, you can get lots of benefits. And as a present for joining, we will also send you 2 10x8 astro photographs taken by our wonderful Space Odysseys astrophotographers. Those of us at Space Odysseys who do astrophotography will send you 2 of those. Hand-picked, hand-selected, hand-reared, wonderful astro images as a present for joining. So head over to patreon.com/Space Oddities, and all the details are there. Once you join Patreon, there's a chat there called New Members, and all the details about how to claim your astro images and download all the Space Oddities material you'll find in that chat. All right, let's move on. It's been a bit of a quiet week for news, so not that much news this week. So just give me a second to sort that out, and we'll have a look at what's been in the news this week. So I hope you can see that. If somebody could just maximize that, that would be great. Okay, so the first thing in the news, it's a picture. It's a lovely picture. I love this picture. I wonder if any of the panel would like to guess what this is a picture of.
Image.
Got no image?
No image. No.
That's interesting. Let me just try that again. Why didn't that work? Okay.
Yeah, we got it now.
Okay. So
just needs expanding.
Okay. So let me just organize myself here then. Okay. Right. Okay, here we go. So this is the first thing I'd like to show you. It's a beautiful image. Any of the panel like to guess what it is?
Looks like the mirrors on the Vera Rubin or something, or
it is the Vera Rubin telescope. You're quite right. What's happening? Any idea?
Are they calibrating it?
They are. That's exactly. You hit the nail on the head. This is the Vera Rubin telescope being calibrated, and by that we mean all the sensors need to be delivering the same quality of image, the same amount of power, if you like. So they use these LED lights to calibrate all the sensors on the Vera Rubin telescope to make sure that all the sensors are doing exactly the same thing. So, but I love that image. It's very colourful, isn't it? It's beautiful.
Very pretty, yeah, very nice.
So, so there we are. We, of course, will get new images from the Vera Rubin telescope later in the year when it finally starts its observing run. And we've already shown you the first test images from the Vera Rubin, which are absolutely stunning. So we're looking forward to many years of amazing images from Vera Rubin. Starting, I think there's currently planning to start the observing run in October, and of course we will keep you fully posted. Okay, so the next thing is that there's been a gravitational wave event. It actually took place in 2023, but details of it have only been released recently because they've spent a long time actually confirming that this is what LIGO and Virga and Cagra saw in this gravitational wave event. Basically what it is, it's the merger of two black holes that has given us the largest resulting black hole of any merger so far discovered. Now, astronomers have known or pretty much suspected that there's this population of intermediate mass black holes between solar mass black holes, anything up to about 100 solar masses, and supermassive black holes, which, as you know, can be millions or billions of solar masses. And astronomers have long been fairly certain that there's an intermediate range of masses that we haven't seen yet. In fact, there have been a couple of strong candidates for it, one of them from another gravitational wave event. But here's another one which has definitively proved that this missing population of black holes existed. And let me tell you a little bit about it. So we start with what happened was that there were two black holes, one with 100 solar masses and one with 140 solar masses. So these were already really, really heavy black holes. And as they rotate around each other, getting closer and closer and closer, eventually spinning around each other at an appreciable percentage of the speed of light, they generate gravitational waves. And what happened in the final merger was that the two of them came together and created a black hole with 225 solar masses. Now, this is now classed as an intermediate mass black hole, as I said, laying between solar mass black holes and supermassive black holes. And this is a really exciting, definitive observation of an intermediate mass black hole. Now, you may remember, if I just go back, that one black hole had 100 solar masses, the other one had 140, but the resulting intermediate mass black hole had only 225 solar masses. So somewhere 15 solar masses have disappeared. And the reason for that is that energy was radiated away in the gravitational waves. So if you think of E equals mc squared, if you think of mass is equivalent to energy, and all of that energy, 15 suns worth of energy. So if you were to convert the sun into energy, 15 suns worth of energy were generated away as gravitational waves in the merger. You have to remember that at the moment, our technology only allows us to detect perhaps the last 10th of a second of the merger. The merger had obviously been going on. The gravitational waves had been emitted for a long time before that. In fact, as we know from Einstein and from what we now know about gravitational waves, any accelerating mass in the universe generates gravitational waves. So even you generate gravitational waves every time you move or do something, any part of your body accelerates, you are generating gravitational waves. And I know I've said this before, but I still find this an incredible thought. So I'm going to say it again. According to Einstein, those gravitational waves never die out completely. They radiate out. So if, for example, if you lift your arm and it accelerates, the gravitational waves from that radiate out across the universe at the speed of light, because we now know that gravitational waves, as Einstein predicted, do travel at the speed of light. And according to theory, they will never die out. So long after you are dead, maybe millions, maybe billions of years, those gravitational waves will still be traveling across the universe. So there'll be a part of you that is forever in the universe, which I think is a lovely thought. The bad news about that is scientists suspect that there will be quantum effects which will eventually dampen those gravitational waves down and erase them, if you like. But the mass on that is not certain. So it's a lovely thought that long after we're all dead, there'll be a record of us in space-time traveling outwards through the universe. Lovely. That's what I think.
How many solar masses again went into this gravitational wave? Did you say?
So you've got you start with 100 solar mass black hole, 140.
Mm-hmm.
When they merge, it came to 225. So it should have been obviously 100 plus 140. It's 240. So 15 solar masses went into the gravitational waves.
So that's something like 30 times 10 to the 47th joules of energy.
Wow.
I just did that on my calculator.
Wow, that is amazing.
It's a lot of joules.
That's an incomprehensible amount of energy. So there we are. So this is good news. So definitively now we have this population of intermediate mass black holes. So I just thought I'd show you that.
Andy, just before you move on,
yeah,
what we're seeing is your PowerPoint page, not your presentation, and
really?
you move on.
What's happening?
No.
Let me just try this again. Let me just try this again. Oh, we're having fun tonight, aren't we? I don't know why that happened. Let's try the right one. Give me 1 second. Sorry about this, viewers. We occasionally have glitches here, as you can imagine. The perils of live broadcasting. Okay, let me just try that again. Right. How's that?
That's better. Yeah, that's it there now. So you're on your third story now.
Yeah. Okay. Right. Let me just get back to that. Oops. Right. So the next story is about NASA's SDO. I don't know if you're familiar with the SDO, Lou.
Solar Dynamics Observatory.
Yeah.
Exactly so. Exactly so. So this has been observing the sun and its magnetic field since 2010. Now, it's got an instrument, obviously, that measures the sun's magnetic field. They've been doing some simulations about what the sun looks like to the instrument on board that measures the sun's magnetic field. And something wasn't quite right. So they did some simulations. They simulated a magnetic field, and they simulated what starlight, or what sunlight coming from the sun, obviously, should look like coming through the magnetic field of the sun. And there was a discrepancy. And they've come to the conclusion, and this is a real shock, that the sun's magnetic field may be twice as strong as we thought it was. Which is an amazing discovery. Because when they did the simulations of sunlight through the sun's magnetic field, it didn't look like anything that the SDO was actually seeing. But thanks to advanced computer simulations, which they've only recently been able to do using supercomputers, it turns out that we may have got the sun's magnetic field all wrong, and it may be twice as strong as we thought it would. Now, Daz, you're like this, obviously, because the implications for studying space weather are enormous, and it might help to explain why we've not been able to predict some recent solar storms. So that's an interesting discovery, if it bears out, of course, that the sun's
it's very interesting.
Maybe twice as strong as we thought it was. So there's that.
May I ask a question?
Yes, of course.
I'm trying to remember. I think SDO has an instrument called HMI.
Yeah.
The helioseismic magnetic imager, I guess.
Yeah.
And so when you first said that, I thought that somehow it was sensing the interplanetary magnetic field generated by the sun, but I think it's looking at things like sunspot regions and getting a Doppler measurement on these to see how much the plasma is being jazzed around by the magnetic field.
Right.
I'm not sure about that.
Right. Interesting.
Okay.
This.
Sorry.
But this is, if it's true, if it's borne out, then this is a fairly major discovery, which will, make astronomers or heliophysicists, have to reconsider what they thought they knew about the sun.
Yeah. My only question is, why hasn't it been noticed by other space assets that are doing not the same thing but similar things, measuring the magnetic output of the sun?
Well, I think it's basically because astronomers didn't have a control, if you like. They just accepted the data was correct. But now that they're able to do these simulations of what the sun's magnetic field should look like and compare it to what's actually being observed, it turns out that it's not the same. So
okay,
we will see. We will see. And then we got the story of missing matter, which is interesting. Now, as you probably know, the universe comprises 70% dark energy, 25% dark matter, and the ordinary so-called baryonic matter, of which we are made and stars and galaxies and planets are made, is only 5%. But there's always appeared to be quite a bit of that 5% missing. We don't know in what form it is. Astronomers have long suspected that it's in very tenuous gas between galaxies that is incredibly difficult to detect. Now, they've been using some new methods to try and detect it recently. One of them, believe it or not, is fast radio bursts. These distant flashes of radio light off in the universe happening all the time in all directions, about which we're still not sure what the origin is. But they've been using those to try and simulate what effect if this tenuous gas is there between galaxies, what effect it would have on the fast radio bursts. And they've actually found this missing matter exactly where they thought it was, this incredibly tenuous gas between galaxies. So the new map of the matter in the universe looks like this. So we've got stars in galaxies, 7% of this 5% of ordinary matter, cold gas in galaxies, 1.8, hot gas in galaxies, 5%, hot gas in galaxy clusters, 4%, cool intergalactic gas, 28%, warm intergalactic gas, 15%, and hot intergalactic gas up to 40%. So in other words, of the 5% of the universe that's made of ordinary baryonic matter, up to 40% of it is this hot gas between the galaxies. So this is great because it solved a lot of questions about where all this matter was in the universe. So I just thought I'd show you that because that's a fairly major discovery that as predicted, the missing matter is between the galaxies in the form of tenuous gas. So interesting, eh?
yeah. That last. Oh, sorry, carry on, Lou.
Lou?
Just that the universe keeps changing every day, every hour, every week. We find something new about it, and the universe looks different.
Absolutely.
Yeah, I think this last story, was the one I was referring to. It was last week or the week before, where they found all this extra matter in the intergalactic things. That same sort of thing. But I couldn't remember what they did to find it. Yeah, so this is probably the same story.
Well, it's not just the method using the fast radio bursts. In fact, they've been employing, I think, 7 or 8 different methods recently, and they all agree that that this is where the missing matter is. Of course, what we're really interested in, let's be honest, is that dark energy and dark matter. That's what we want to know desperately. But we, Lou and I have long said that we want to have a debate about this dark matter versus MOND here on Space Oddities. So, Lou, we must really pencil that in for some point.
Absolutely, and we have penciled in, as I think you all know, a noted, highly noted astronomy author who will be coming on our show. I won't mention their name, but I am having lunch with them tomorrow, and I am going to dive deep into this issue of dark matter. This is an infrared astrophysicist, so we'll keep that as a secret for now. But
fantastic. So, talking of guests, on the 2nd of September, we will be delighted to welcome Nicholas Booth as our special guest. He is a science writer. He's co-author of a wonderful book called The Search for Life on Mars. Now, this brings us, of course, into the subject of Mars Month, because that will be the first live stream in September. And as we have said, September on Space Oddities is Mars Month. We'll be doing live streams and hopefully a lot of videos all about the planet Mars. And Nicholas Booth will be our first guest to talk about this whole subject of life on Mars. So that's the 2nd of September, the first live stream in September. and we hope you'll join us for that, because he's a wonderful writer, and we can't wait to talk to him. So don't forget, Mars Month, September, on Space Oddities. If you're at all interested in Mars, we'll tell you a lot about Mars all through September. And we did Moon Month in April, we're doing Mars Month in September. So if there's any other month that you would like us to do, a themed month if you like, then put it in the chat, because we are always open to suggestions. And if you want to make any suggestions about what to include on Space Oddities, you are welcome to email us at any time at info@spaceoddities.space. Check out the website as well at https spaceoddities.space, and of course we'll be very grateful for your support. So Sea Star Month, yes, very good, Lou. How can I put this? No. So there we are. Comment from Ian here. The popular science people suggested that it was the dark matter that had been found rather than explaining the baryonic matter. Yeah, they would, wouldn't they? Because they don't have a clue what they're talking about, Ian. But trust me, it's not. This is the detection of the missing baryonic matter. So thank you for that.
Yeah, we just haven't really had the technology or the where to actually find this. But we know that there is baryonic matter missing.
Yeah.
But now we've this is a clue to where it is. And it has been imaged using I think it was might have been X-rays or something, or infrared. I think it was low infrared waves, and they were able to pick out where the intergalactic gas is.
Yeah.
And of course, and this is just a step on of what's actually that gas it is. So it's
right.
As you said, it's a very interesting story, and this could also like you say, the dark matter and the MOND scenarios could tweak them, and we'll see what happens.
Yeah.
Yeah, very interesting.
So can I just say hello to a few people? Hi, Melinda. Thank you for joining us. Hi, Anne. Thank you for joining us as well. You're most welcome. We've had a suggestion of Jupiter month from Ian. Oh, Lou, you're going to love this. Stuart says Titan month. So you may know, Stuart, or you may not. Lou, as a planetary scientist, is a specialist in Titan. It's his baby, if you like. And we'll definitely give that some thought. I know what Lou will be voting. So mind you, he can do all the work for it, can't he? So as it's his baby. So there we are. All right, then. Let's move on. We're going to move on now to a man who has often been described. We're going to move on to Roger, and with the gallery and the Night Sky Guide. Roger, can you hear us okay now?
Can you hear me?
Yeah, we can.
Yeah. Thank you.
Sadly, yes.
Yeah.
Well, I mean, yes.
Oh, don't be cruel. He doesn't get out very often.
No.
So there we are. Okay. All right. Well, there we are. Let me put this up for you, Roger, and we'll see what you've got for us this month.
Yeah, well, we're transversing from July into August over the next week. So there we go. And conversely, we're working our way through the phases of the moon, coming up to our first quarter, leading up to the weekend for those selenophiles like me. And during the night sky, should there be any clear visibility, we've got the great Milky Way coming out through from the southern hemisphere, leading almost to overhead where we've got the summer triangle. Wow.
Fantastic.
There we go. But as the night goes on, we are visited again by the planet Saturn. So it's managed to zoom away from the morning skies and start to come back into the evening skies again. It won't be as high as it was previously, but we will have the opportunity again to see Saturn and the rings, and they will be starting to widen very slightly. So things are looking a bit better for that. But if you want to see anything in the morning, we do still have Uranus, which is just south of the Pleiades. And then further on, we will have the greatly shining planets of Venus and Jupiter coming up before the sunrise. But as Lou was saying before we started, we've got some meteor showers coming up. And obviously, we've got the great Perseids, which will be coming up in the first half of the month. We've also got Venus and Jupiter coming closely together again to see in the morning skies. Mercury will also be coming at its greatest elongation on the 19th, and then there'll be a black moon on the 23rd of August.
What's a black moon?
A black moon. I'm glad you asked me that.
Yeah, I'm glad as well.
Right, now a black moon is a bit of a rarity. It is a new moon, and its justification as a black moon is that there is 3 new moons in a season. So that occurs about every 29 months. So not as often as some of these blue moons and things like that. So it's when you get quite a few new moons in a season. So that's the reason for that. So
it's the same as the blue moon under the old method of calculating it.
Yes,
but it's for the new moon.
Yes, rather than the full moon.
So it's 2 new moons in 1 month, basically.
No,
not quite.
It's under the old system, where you basically go and look at the PowerPoint, Andy.
Yeah. There's a seasonal black moon, and then there's the other one. So the seasonal black moon defined as a 3rd new moon in the season of 4 new moons.
Right.
These black moons are a little rarer and occur once every 33 months. Earth seasons are about 3 months and are typically have 3 new moons, but sometimes the season has 4 new moons. So the
I see.
3rd moon is called a black moon. So obviously cross that one off and count the 4th one as the 3rd.
I see. Oh, well, thank you for that, Roger. I've never heard of that before.
No.
It works on the same principle as I said, the blue moon. You've got 3 in each season, if you know what I mean, because it's divided into 4. The year is divided into 4 portions. Of course, you've got sort of winter, autumn, summer, and all like that. And you can only have you should only have 3 full moons and 3 new moons, but because of that all the months are not the same, they tend to move around. And you should only have an early moon, then you've got a new moon or a full moon, or you've got a late full moon. And it's when you get the 4th one slip in, they make the 3rd one, as Roger said, they make the 3rd one a black moon if it's a new moon, or a blue moon if it's a full moon. So it's a bit complicated. We have got a show up about it. So if you'd like to go and find it, it's in I think it's in the basics.
Right.
Course. So have a look. It's because the theory, the one that you said, Andy, about doing 2 new moons in a full month, because that making it the black moon.
Yeah.
That was a misreading of the actual rules regarding this, because it's also to do with church calendars and things like that. It's to keep basically that you've got the early, then you've got the full, then you've got the late. So you want to keep the 3 going there. So you had to name the imposter, or it moved in as something else, and it's always the 3rd one, not the 4th one. So they all stay the same. It's a bit complicated. Have a look at the PowerPoint that we produced on it, and then you'll be able. It's a bit long-winded. So
well, I mean, yeah, but you know, the whole dynamics of the moon and its phases and the seasons and the months it's quite complicated when you think about it, isn't it?
That's right. Yeah, it's the fact that the moon, the months are not 28 days.
No, that's true.
And of course, the actual orbit of the actual moon is not 31 days. So you tend to get one creep in occasionally.
Okay.
Well, there are actually 4 definitions for a lunar month, right? There's the sidereal month, the synodic month, the draconic month, and the anomalistic month. And that's important, probably not at all, but it is important if you are calculating the Saros cycle of solar eclipses.
Right.
Take all those into the equation, the resonances between those. So there you go.
See, look at the can of worms Roger's opened.
Sorry. There we are. We've all learned something tonight.
Absolutely. Exactly. Which is what it's all about.
Absolutely. Right.
Just go to sleep, Roger. We'll take it from here. We'll do
Right.
No, I'm just
on with the show.
Right.
And we're on to the gallery, eh? Woohoo. Let's see what we've got from our wonderful viewers that have subscribed and put their pictures in. And our first one is from our very regular Jerry DeLay, which is of the Cygnus wall with his usual setup of his 6-inch telescope and his 2600. And this is what he's managed to produce of the Cygnus.
Oh, Jerry, another winner.
What stunning.
Stunning.
Got a lovely image there.
That's beautiful. Wow.
Wow. Goody good. And onwards with the next person. And we've got a rather nice sunset from Ian McIntyre, which he took with his phone.
Oh, that's
nice.
Hey, that's great.
Got some lovely colours there.
Yeah, beautiful.
Yeah.
Well done, Ian. It's great.
Very nice. Well done, Ian. And we've got some interesting sunsets here from Kenneth. Now, these are multiple stitch panoramas, which he's put together. One of the sunset itself and another one just after sunset. And these are some views that he's done from his country in Norway.
How beautiful.
Oh,
Lovely.
wow. That's very atmospheric, isn't it?
These are all vertical panoramas. So they're all stitched up together and make such a very wide landscape.
Well done, Kev. They're beautiful. Beautiful.
Yeah. And then to top it off after those, he's got a little glass orb, which adds to the effect of his landscapes here. And it went a bit quick there. There we go.
Oh,
Wow.
That's lovely. They're really.
So we've got inverted images in the globe, obviously.
how cool is that?
That's really cool. Real crystal ball stuff.
Yeah. Be interested to see if I haven't seen Kenneth do one, but it'd be interested to see if we could get a Milky Way in an orb shot as well.
That would be great, wouldn't it?
That'd be.
I think that gives Kenneth job away during the day as a fortune teller.
Yeah.
Well, at least it's not a snow globe.
Yeah. Well done, Kenneth.
Yeah, thank you, Kenneth.
That's lovely.
Right. And then he's just got another sunset on one of the lakes, another little stitch up of some pictures of another sunset. So he's obviously getting some rather interesting views there.
That's gorgeous.
Lake.
Certainly is.
If you can't photograph without the clouds, photograph the clouds instead.
Exactly. Well done. Well done,
Beautiful.
Beautiful. Beautiful. Beautiful.
Yes. Very dramatic. And oh dear, there's some from me.
Oh God, here we go.
Right, shall we switch it off now?
Yeah. Well, thank you for being with us tonight, viewers. We will see you next week on Space Odyssey.
Now, these were done on my iPhone, so it just gives you an idea of how we can do some Milky Way shots. And on the one on the right, you can actually see the Andromeda Galaxy there, right in the center of the frame.
So this is with your iPhone, did you say, Rod?
iPhone 16. Although the one of the Andromeda is with one of the little telephoto lenses.
Oh, okay, then that makes sense.
Yes. And these were 30-second images just processed from the phone. So,
And taken from the same location around
yes,
the
from my garden.
Wow.
I just turned it round and there it was.
Absolutely amazing, Roger.
Yes, it's certainly moving on. I mean, it's not a Samsung quality picture, but the iPhone has done pretty well.
That's good enough. That's fantastic. That's nice.
A for effort.
For a 30-second exposure, I've got no star trails on that.
No.
How did that happen?
Gorgeous.
That's amazing.
Yes.
Well
Anyway,
done.
so and then I've got one of my many pictures of the moon. This was taken in the afternoon, so I had to use an infrared filter to try and get the contrast. There wasn't much difference in the contrast between the sky and the moon at that point. So
that's gorgeous.
So that's not coming.
Well, that worked, didn't it?
It certainly did.
Wow, beautiful, Roger.
And then we've got one of our local star, which was done yesterday, and it was some interesting prominences on there yesterday. So I thought I'd just try and grab a little bit, and there we go. Yeah. This was through some breaks in the clouds, so I couldn't quite do a big stitch of all the images together to make a whole disc, but I just managed to get this one, as that's what most of the prominences I could get in on one go.
Lovely.
And did you say at one point that you take one image of the solar disk and another image with different integration times and so on for the prominences? Is that
no? This was all done in one go.
Wow.
I use a program called IMPPG, which with careful curve manipulation, you can bring out the prominences just as well with the surface detail at the same time.
Holy moly. That's amazing.
It is amazing. Well done, Rog.
Yeah, and also in the bottom right corner, you've got a prominence there, a filament, haven't you?
Filament there, yeah. Yeah, I mean, there is a little bit more activity at the moment, but obviously the weather has proved against me again to be able to get them. But there are lots more smaller sunspots about again.
Yeah, lots.
So obviously some that have managed to come round from previous attempts on previous orbits. So should be good.
Fantastic.
And that's what we've got for this week.
Okay, thank you very much, Roger. That's really good. So
I know we'll be talking about the sun in a while, but as Roger said, there is the sun has become very active again with sunspots. But have you noticed, Roger, that at the moment they're all in the southern hemisphere?
Yes, and there have been quite a few coronal holes as well, haven't there?
Yeah, very big ones, which has been very interesting. Because we thought, well, we assumed that we were now in the decline of the cycle. But last month and this month, and we'll be getting the new figures for the sunspot count for this month in a few days' time. There was a very sharp rise again last month, and I'm wondering if it's going to continue this month, and so it's going to climb again.
Yeah,
because
sort of like
the month so because it dropped very, very low, and it was even below predicted levels. So it's very interesting to what the sun's doing at the moment.
Sure.
So, but we'll have a chat later.
Yeah. Okay. Well, moving on. Before we go to Lou and the Battle of the Exobots, which is his thing tonight, I'm going to talk to you about the precursor and pathfinder telescopes of the Square Kilometre Array. You may remember we started looking at the SKA last week, and this is just the second part of it. So just let me. So I hope you can see that. And somebody can maximize that. So just a quick revision in case you weren't watching last week. The Square Kilometre Array is the most ambitious radio astronomy project to date. In fact, in terms of its sheer size, its physical size, it's the biggest scientific project that humans have ever built. So what this presentation is about is the so-called precursor and pathfinder telescopes, which are basically to test technologies that will be used in the completed Square Kilometre Array, but they've also been making some great discoveries in their own right. So let's have a look and see what this is all about. So precursor telescopes are located at the same sites as the SKA, and that is, as you will have learned last week, in South Africa or Australia, and they are directly contributing to the design and the development of the SKA infrastructure and technologies. So their key characteristics are that they're located in either of the two sites, South Africa and Western Australia. They contribute directly to SKA hardware and software design. They often use SKA-like instrumentation and infrastructure, and they serve as test beds for scientific and technical operations. For example, the Meerkat telescope in South Africa, which is a precursor for the SKA mid-frequency array in South Africa. The SKA is divided into mid-frequency antennae in South Africa and low-frequency antennae in Western Australia. You've also got ASCAP in Australia, which not surprisingly is a precursor for the SKA low, and the MWA, the Murchison Wide Field Array in Western Australia, and this is an early low-frequency science and infrastructure precursor in Australia. Pathfinder telescopes, on the other hand, are not necessarily located at the SKA locations in Australia and South Africa, but they're independent national or international projects that explore and develop key technologies, techniques, or science goals relevant to the SKA. They may be located anywhere globally. They contribute to technological or scientific development relevant to the SKA. They're not part of the SKA infrastructure, but often collaborate closely. And they explore techniques in signal processing, calibration, antenna design, etc. Examples is the European LOFAR network, based in Netherlands, but also spreading across Europe, which is low-frequency science. You've got eMerlin, the network in the United Kingdom, which is high-resolution imaging by connected radio telescopes. And, of course, as shown in the image, China's giant radio telescope, FAST, large single-dish design and sensitivity studies. FAST at the moment is the biggest radio telescope in the world, but, of course, the SKA, in terms of its sheer size across the two continents in South Africa and Australia, is going to be a lot bigger. And you've also got JVLA in the USA testing advanced interferometry techniques. Now, interferometry is basically the process of joining the different antennae together virtually to form one giant receiver. So the purpose and impact of these Pathfinder networks basically to test technology, and I don't want to get too technical, but just in case you're interested, including phased array feeds, wideband single pixel feeds, and advanced digital signal processing systems, operational insights. This is to get experience in handling massive amounts of data amounting to petabytes per day that is going to stream from the SKA when it's completed in maybe about 5 years for the first phase of the telescope. And developing data processing pipelines. Don't forget that when the SKA is completed at any one moment, it's going to be processing more data than the whole of the internet. So it's these vast amounts of data, and this is what the Pathfinder networks are used for advancing that technology, and of course to test engineering solutions. So the Meerkat telescope, as shown in the image, it's 64 dishes, each 13.5 meter in diameter, and they're all steerable as well. And they can be set up to form a long baseline of 7,700 meters. And just some technical information about the frequencies that they cover. It's one of the most advanced radio telescopes in the Southern Hemisphere, and it will be integrated into the SKA mid array. So the Meerkat radio telescope became operational in 2018. In 2019, this was the radio telescope that discovered these enormous radio bubbles spewing out of the Milky Way's core, spanning 430 parsecs. This is probably, although it's not definite, but probably the activity associated with Sagittarius A star, the supermassive black hole at the center of the galaxy. And since 2020, it's been conducting major survey operations. And its exceptional sensitivity and dynamic range have enabled groundbreaking observations of neutron hydrogen pulsars and radio galaxies, and establishing new benchmark for radio astronomy performance. So don't forget, this would be just a part of the SKA, and already it's made these major discoveries. ASCAP has not been slacking either. This is 36 dishes, each 12 meters in diameter. And it's got a 30-degree field of view compared to 1 degree for traditional feeds. And it catalogued over 300,000 galaxies in just 1 year, detected hundreds of fast radio bursts. I talked about fast radio bursts earlier. These immensely powerful flashes of radio light lasting a fraction of a second that we see all over the universe all the time. We don't know what they are, but the leading contender at the moment is magnetars, these neutron stars with unbelievably intense magnetic fields. And it's been used to trace magnetic fields in the Milky Way and nearby galaxies. And it's pioneered the use of phased array feed technology. And if you want to know what that is, you can easily Google that and find out if you want to go into it in more detail. Hera as well, the Cosmic Dawn Explorer. 350 fixed 14-meter wire mesh dishes. This is probing the era of epoch, I should say, of reionization, detecting primordial hydrogen signals and mapping the universe's first stars and galaxies. LOFAR in Europe, 20,000 antennas distributed across 52 stations in the Netherlands, Germany, Poland, UK, France, Sweden, Ireland, Latvia, and Italy. And it operates in 2 bands, the low band and the high band. It's had a big scientific impact. It's mapped cosmic magnetism on intergalactic scales and created the most detailed low-frequency sky survey containing over 4 million radio sources. And it's been pioneering data processing, handling 13 terabits per second of raw data through a supercomputer in the Netherlands. 13 terabits per second is a huge amount of data to process in a second. So this is what LOFAR is used for. And some scientific discoveries from the Pathfinders, these galactic bubbles, as I said, these weird radio bubbles coming out of the center of the Milky Way, thought to be associated with Sagittarius A star, as I said. ASCAP has, since it went online, the number of fast radio bursts that have been detected has risen by a factor of 50. So ASCAP is really good at detecting these fast radio bursts and helping us to establish their origins. And here, the Cosmic Dawn Telescope has set the most stringent constraints on the temperature of the early universe, providing insights into the formation of the first stars. So Pathfinder telescopes are not just technology testbeds, but powerful scientific instruments in their own right, making substantial contributions from astronomy. The legacy and impact of these number one, has helped to shape the SKA's key science projects and observational strategies, technical validation of new technologies, helping to establish this incredible data infrastructure that's needed to process that gargantuan amount of data. And it's established effective international scientific partnerships across 16 plus countries that will carry on into the full operation of the SKA. So that's it. That's just a look at the Pathfinder and precursor telescopes of the Square Kilometre Array.
Michael's joined us.
Oh, good God, he's back. Hello, Michael. How are you this evening? We can't hear you.
Hello.
Oh, there you are. God, I thought you got a case of Roger Arthur. Yeah.
Obviously, the restraining order didn't work.
Oi.
Someone left the back door open. Just back to your content there, Andy. Did you read recently that using, I don't know whether it was Meerkat or Pathfinder or whatever, they've been looking at satellite constellations and that they're finding now that they were looking at, I don't think it was specifically SpaceX, but they found a lot of the SpaceX satellites are leaking, how can I say, radio waves at the same the wavelength that they're using, which is
Yes,
supposed to be
I did see
protected.
this. Yes.
Yeah, and apparently they think what it is, it's not deliberate.
No.
It's actually noise from the instruments inside the actual satellites
Mhm.
themselves. So this could
Yeah.
become a problem. So it'll be interesting to see what happens there.
It will be. And this, again, just demonstrates that Starlink satellites should never have been launched without evaluating the impact on not just optical astronomy, but on radio astronomy as well. But yeah, the radio astronomers are really concerned about the Starlink satellites and their interference in the radio bands that the SKA will study.
And also, I mean, optical telescopes, they end up with a big line through them because in the optical wavelengths, because when a satellite goes over,
yeah.
So it's a
Starlink,
strange.
I see that last week the whole Starlink network went down.
Yeah, for a few hours.
For a few hours, yeah. I don't know why they haven't announced a cause, but something. So I think it was software related. But there we are. But you know, this is just the beginning, because so many countries want to put these vast satellite constellations in orbit. China have got plans. Of course, we know that Project Kuiper, Amazon's plan to launch a mega constellation of satellites for internet provision. And you know, there should be international laws about the design of those satellites, but there aren't, and it's caught astronomers off guard a little bit, and they're playing catch up, trying to mediate the actual damage that can be done.
Yeah, well, maybe there'll be an answer in what I'm going to talk about a little bit later on. If we have a big flare, some of these will be coming down anyway.
Well, I mean, lots of the Starlink satellites are coming down anyway every month. So you know, I personally, I think the idea behind it is a great idea to provide internet coverage to people in the world that have never had it before or have got really bad internet connections. I really applaud that, because you know, literally a couple of billion people on this planet have not got any sort of internet, and they are disenfranchised from the rest of the world, can't really participate and communicate with the rest of the world because of it. So it's a great idea, but you know, it should have been examined because of the potential effects on astronomy. But you know, there aren't many people in the world who give a damn about that, unfortunately. So so there we are. So anyway, good to see Michael here. Glad you got the tag off your ankle eventually. And
it wasn't a proper meeting.
yeah, right. Yeah.
Federation of Astronomical Societies.
And how did the meeting go?
Fine. Yes.
Good.
Yes.
Okay, great. Well, moving on now, we're going to go over to Lou for Battle of the Exobots, which is really interesting. So, Lou, you can definitely take it away, sir.
Yes, sir. Battle of the Exobots today. 2 planet hunters, over 2,000 new worlds.
Wow.
Yeah, this is serious stuff, guys.
Sexy.
Okay, so the exobots we will be looking at today. On the left, we have the Kepler mission, the original exobot telescope in space. And on the right, we have the TESS spacecraft, the transiting extrasolar survey satellite. That is the contender. And so we will see who wins this battle. This is just an outline of a number of space telescopes that are either primarily aimed at exoplanet discoveries, or that who can do exoplanet discoveries as a part of a wider and broader set of science objectives. All of these telescopes, from Hubble to James Webb, and I should mention that James Webb is often referred to as one of the New World's telescopes, advanced telescopes. But all of these are mentioned as priorities in the astrophysics decadal surveys, both in 2000, 2001, and in 2010. So these are priorities for the astrophysics community. All right, if you have been around for a while as our audience on Space Oddities, you will know a little bit about how we detect extrasolar planets. There are a variety of detection methods. Most of them are indirect, like watching the planet wobble, or the star that's being orbited wobble back and forth, or wobble side to side, or perhaps using general relativity for microlensing, those kinds of things. But by far the most what's the word I want? The one that has borne the most fruit, the technique borne the most fruit, is the transit detection method. And on this graph here, you can see a few things. You see the launch of Kepler, and you see the launch of TESS. The horizontal arrows indicate those various missions' lifetimes. So Kepler launched in 2009, and it's both its original mission and its extended mission in 2018. And then TESS launched in 2020, in December 2020, and extended its mission for about 5 years. The purple in this graph, in this graphic, are the numbers of exoplanet detections from the transit detection method. And the lion's share, as they say, of these detections in purple were from the Kepler mission and the TESS mission.
Lou, can I just ask you a question about the transit method?
Yeah.
We can, of course, only see exoplanets when they transit across the face of the star.
Correct.
But that means that their orbit, if you like, is, if you like, edge onto us. Yeah. So presumably, we're missing a lot of exoplanets whose orbits do not take them across the face of their star, as seen from the Earth.
We are. We most certainly are. And this is why other detection methods, most notably the radial detection method, which I think is in green here. Yes, the radial detection method in green is the second most fruitful method of detecting extrasolar planets. Here we see the planet the star that the planet is orbiting being tugged away from us and toward us. And by analyzing the Doppler shift of the spectrum of that star, then we can tell that there's a planet orbiting it. But you are absolutely right. This also means that the transit detection method is fairly sensitive to not only the inclination of the orbit, but the size of the planet and how closely the planet orbits. Yeah. If you have a planet that's orbiting very close to its star, the odds of seeing the star in eclipse are better. If you have a very large planet orbiting the star, the odds of seeing the star in eclipse are better. So the transit detection method works better in those scenarios. And of course, the nice thing about the transit detection method is that it's not distance dependent. If you're going to use astrometry, for example, and watch the star wiggle back and forth as the planet orbits, you're only going to be able to do that out to a certain distance. So each of these methods, as you are so accurately bringing out here, Andy, each of these methods has their strengths and weaknesses.
Sure, thank you.
So just a quick look at the two missions. Kepler launched in 2009 from Kennedy Space Center, and it is in an Earth-trailing orbit. So it is slightly outside the Earth's orbit, orbiting the sun. It's in a heliocentric orbit, just kind of trailing behind the Earth. Kepler, which was the first exoplanet focused mission stared at just one area of the sky in the constellation of Cygnus, the Swan. And that was its prime mission, to open the aperture and get as many detections as possible from very faint stars from just that one area of space. Now, it turns out that Kepler had some difficulties. It lost some of its reaction wheels. And so they kind of, in what was called the K2 mission, the extended mission, they started looking at a wider region of space to be able to provide still some science, even though they're only operating on 2 reaction wheels. But primarily, it was focused on one area of space. It found over 2,000 exoplanets. The actual number of confirmed planets that you see on the bottom left there is 2,662. And then still a number of candidate planets in addition that are still being evaluated. So limited sky coverage, as we mentioned, and was able, because it focused only on one area of sky, was able to find a large number of exoplanets orbiting their stars because they were able to see very faint stars. TESS, on the other hand, had a little different approach. It turns out very nicely that around the time that Kepler's extended mission was ending, TESS was beginning. So it really is the follow-on to Kepler. Launched in 2018 from Kennedy Space Center, but not in a heliocentric orbit. This is in a 2-to-1 lunar resonant orbit, often called P/2 or P over 2. It orbits the Earth out to about the orbit of the Moon, but orbits twice for every one orbit of the Moon. So about every 2 weeks it orbits. And this allows it to see a very large swath of the sky. This TESS is more of a wide field survey. It observed many areas of the sky. In fact, to date, they've been able to analyze about 85% of the sky. Now, not with as long integration times. These are mostly nearby stars or fairly nearby stars, but much wider coverage. So TESS mission see a lot of the sky, but only focus on brighter nearby stars, which then would allow much easier follow-up from ground-based telescopes, perhaps even amateur telescopes. So shorter observation period. It discovered 643 absolute detections of exoplanets, but there are over 7,000 candidate detections that are waiting for follow-up observations to be verified. So both instruments, slightly different science objectives, both clearly contributors to our understanding of worlds outside the Earth. Just a little architecture for the 2 spacecraft. You can see on the left the Kepler spacecraft, focusing on some of its reaction wheels. Again, when it ended its mission, only 2 were working out of the 4. Its communications subsystem, the photometer, which is what detects the light from the stars, a star tracker to keep it pointed very accurately, and its solar power array. On the right, we see the TESS instrument, also with reaction wheels. Oh, I should mention both TESS and Kepler not only had reaction wheels for pointing, but also had thrusters. And as Kepler lost its reaction wheels, by changing the mission objectives slightly, looking through more or less the ecliptic plane, they were able to use the reaction wheels and the thrusters and solar radiation pressure, believe it or not, as small as that is, to stabilize the pointing of the instrument. So pretty fascinating stuff. So on the right, the TESS instrument, you see its solar arrays, Its CPU, its master computer there, the propulsion tank for its thrusters. You can see here where the reaction wheels are, and the cameras are inside the center of this spacecraft. You can see the lens and the camera hood and detectors and so on. As we mentioned, on the left, we have the Kepler field of view for its primary mission. Again, it was extended. Its extended mission, by the way, was called K2. But for the primary mission, it viewed stars just in this little pattern here in the constellation of Cygnus. For the TESS instrument, it scanned the sky with these 4 arrays here you can see, and it would scan each part of the sky periodically and then download those images for analysis. So just a little, these are the Madison Avenue PR slides that the missions put out, kind of fancy. Kepler spent about 10 years in operation over its primary and extended mission. Observed 530 million stars, confirmed 2,662 planets, with others waiting for confirmation, and was in a, as we mentioned, in a heliocentric Earth trailing orbit. TESS, this is an older TESS diagram, so there are about twice as many confirmed planets as we see here, and over 7,000 confirmed, 7,000 candidates. So this is a little bit old. Each of those missions spawned a number of research papers. This is the big number on the lower left here. 93% of the sky was observed by TESS. And you can see here some multinational mission, and observed almost 500,000.
50 nations. That's amazing.
Yeah.
Just you know, again, underlining how truly international modern astronomy is.
I imagine that this is a combination of the teams that built the spacecraft, the science instrument teams that received the data initially, and then the wider scientific community that helped with the analysis and confirmation.
Sure.
So,
Sure.
So that is the battle of the exobots. What say ye? What say ye, Space Oddities fans?
Well, I would always have a special affection for Kepler, it must be said, because it lasted for 10 years, and you know the sheer number of candidates it discovered for exoplanets. I'm sure you know TESS is doing a fantastic job, but I'll always have a soft spot for Kepler.
Yeah,
Kepler was an amazing mission, and it was the first dedicated. That's the word I'd been looking for. The first dedicated exoplanet mission.
True, very true. Yeah, absolutely, absolutely. So there we are. I just want to pick up on a question that came from Ian about the SKA. He said, does any of this help with SETI? Most definitely, Ian. One of the prime scientific objectives of SETI is to try and detect artificial signals coming from exoplanets. And just to give you an idea of the sensitivity of this, if you can imagine an airport radar and assume that extraterrestrials would also have airports, would also have airport radars, the SKA would be able to detect the airport radar on a planet 20 light years away. So it's, yeah, so that gives you some idea of the immense sensitivity of this instrument, 100 times more sensitive than any existing radio telescope. So SETI is very much a part of the SKA's goal. So there we are. Well, thank you for that, Lou.
Lovely. Yeah, great.
Now we have one vote for Kepler, I see. Stuart.
Yeah, good man. Good man. Kepler's definitely the one I would plumb for. What about you, team? What about you, Daz? What do you think?
Yeah, Kepler.
Kepler. Yeah.
Well, I'm a softie for these old telescopes and things like that. So,
Kepler's for me as well.
I mean, Tess is doing a wonderful job. Don't get me wrong.
Yeah.
But I mean, Kepler has done its job. It was extended. It carried on with its discoveries. I mean, Tess, if they extend it even more, maybe it'll be, even more successful.
And of course, Tess is normally one of our viewers as well. But I don't think she's on tonight.
That's right. So, what about you, Michael? Kepler or Tess?
Kepler. Yeah.
You've got a fascination for old.
Yeah.
So there we are. So anyway, moving on. Thanks viewers for that. Thank you, Falou, for another fascinating battle of the bots, and there we have it. So where do we go from here? Well, we go over to Roger now for Constellation of the Week fanfare. So who have we got this what constellation have we got this week?
We have Virgo.
Da-da-da.
Da-da-da. Right, so here we go. For those, I won't read the first line of the sentence of the top there.
Right.
We all know what that is. We don't go there. Anyway, it means maiden in Latin, and there's traditional astrological sets. So between Leo and to the west of Libra, lying in the south, it's the second largest constellation in the sky.
Wow.
After Hydra.
And the largest one in the zodiac. Wow.
Yes, absolutely.
Not a lot of people know that.
Not a lot of people know that. They do now.
Yeah.
So the eclipse intersects the celestial equator through this constellation, and the sun passes directly overhead of the equator in this constellation at the September equinox. So Virgo can easily be found with its brightest star, Spica, in Latin, grain-headed.
What does that mean?
So here we have a depiction of Virgo as a person. So early Greek astronomy associated Babylonian constellation with their goddess of wheat, agriculture, and autumn, Demeter. So the Romans associated it with their goddess Ceres. Alternatively, the constellation was sometimes identified as the virgin goddess Lustistia or Astrea, holding the scales of justice in her hand.
Wow.
Now are separated as the constellation Libra.
Interesting.
So another Greek myth from later classical times identifies Virgo as Erigon, daughter of Icarus of Athens. Icarus, who has been favored by Dionysus and was killed by his shepherds while they were intoxicated, after which Erigon hanged herself in grief.
That's a pretty low trick, killing somebody,
I
isn't it?
know. Yeah. They're all very desperate, these things. It sounds like an episode of EastEnders or something.
When Daz and I used to do the Amazing Astronomical Alphabet on Astro Radio, we came across some of these stories in ancient myths, and so a lot of them were quite gruesome, weren't they, Daz?
Oh, really? Just a tad.
Yeah.
Lots of killings, poisonings, and things like that going on.
What was that one about? This was the Greek myth of the girl who was covered over and led up a hill and then pushed off a cliff. Do you remember that one? I mean, it was just.
Yeah, there are so many. Many.
Gosh.
It's yeah. I mean, when you look into these Greek mythology things, they are. It's a bit like the Bible, and that can be quite gruesome in places.
Absolutely.
So,
they did know how to spin a yarn, the ancient Greeks, didn't they?
Yeah. I mean, when you go back to the Titans, that was one dysfunctional family.
Yeah.
That really was. Really was.
Yeah. Sorry, Roger. Please carry on.
Oh, well, there we go. So another figure who was associated with the constellation Virgo was the spring goddess Persephone, the daughter of Zeus and Demeter, who had married Hades and resided in the underworld. So there we go. So everyone's got their own versions of how these constellations are made up and their stories. So we've got the basics of the constellation here. And the brightest one is obviously Spica, which is just under magnitude 1. And then the magnitudes fade somewhat up to nearly magnitude 3 for some of these other stars. So it's not exactly easy to spot, but once you get to recognize the sort of the bowl shape of the constellation, then it does become quite recognizable. Obviously, following on from Leo, which is also full of all these wonderful galaxies and stuff, as you will see in a minute.
Yeah.
So just a few more facts here. Virgo is prominent during in the northern hemisphere through March and April. It's the largest zodiacal sign, and the sun takes 44 days to travel through it.
Wow.
Longer than any other. So, and it says from here, from 1990 until 2062, this will take place from 16th of September to the 30th of October.
Wow. That is a long passage.
And it can be seen through the latitudes plus 80 and minus 80 degrees. So there is a fair good percentage of those people that can actually see it quite easily. So we obviously got one of the main constellations with all these galaxy clusters here, and most of them are within the borders of Epsilon Virgus, which is called Vinda Matrix.
Of course it is.
Yes. Sounds a bit kinky to me, but there we go. Okay, so we go through some of the details of these constellations. A lot of people will already be aware of these. M87, which most people will know, major radio source and 60 million light years away. And it's got some rather interesting objects, which has also got to black holes there, which on the 10th of April 2019 managed to release an image, which we did show on previous editions of our show. And here's one of the images over here on the right, and the other one showing the emissions from that area as well.
And just to put a figure on it, that jet, there are actually two jets that shoot out of the core of M87 from that black hole. You can see the jets at these 11 o'clock and 4 o'clock position, but optically the other jet is drowned out by the light of the galaxy because it's pointing away from us, so it's not that prominent. But you can see in radio wavelengths here very clearly in the famous image. That jet that you see in the image on the left, the optical image, 5,000 light years long. So it's absolutely immense.
It is, absolutely. And then we go on to another Messier object. There are quite a few Messier objects in this constellation. M60, an elliptical galaxy, 57 million light years away. And with this other one, NGC4, forms a pair known as ARP116. Nearby to M60 is M59, which is quite handy.
Yeah.
It's discovered by John Gottfried Keeler in April 1779, and he was observing a comet in the same part of the sky. So that's obviously why Charles Messier added it to his catalogue about 3 days after. So
you can imagine him saying, "Right, I'm nicking those."
Yeah. The one was an actual comet. The other one was the galaxy. So
right.
So there we are. Because they were so close, he thought they were both comets, I guess.
I bet Messier was annoyed because he was known as the ferreter of comets.
Yeah,
that was his main task, and the reason for the Messier catalogue was to mark things that can be mistaken for. Fuzzy blobs that could be mistaken for comets, so that he doesn't keep repeating the same mistakes.
The original Messier catalogue was published in 1783, and I wonder what he would think today that his catalogue is still the standard catalogue for deep sky objects.
Yeah.
Yeah.
Especially when you want to do a Messier marathon in March as well.
Yeah, but that's changed now. It's now known as the Messier Snickers. So
Okay. Yes.
Wah, wah.
The chocolate bars are available.
Yeah.
Okay, so after we've gotten that onto there, we've gone on to M84, which is a giant elliptical lenticular galaxy. And Charles Messier discovered that in 1781 in his search for nebulous objects in the night sky. So it has a morphology classification of an E1, denoting it has flattened about 10%. So there we go. So
Wow.
what? It has got a massive dark matter halo around it as well.
Mm.
There
Fantastic.
we go. Yes. So there we go. There's a... Ooh. And then we've got the infamous Sombrero Galaxy, M104, which is quite a good photography image. So that's between 94... oh, God, hang on. Keeps going okay. Between 95 and 105 light years in diameter. 105,000. So sort of slightly bigger in size than the Milky Way, maybe, but it's 31 million light years away, and is part of the Virgo 2 group.
And as it says, the classification of the Sombrero Galaxy is a little bit unclear, isn't it? Because if you look at the image, you've got obviously that giant dust ring surrounding it, but it doesn't really fit neatly into any galaxy classification.
No.
So yeah, interesting.
It's quite distinctive with that dust cloud all the way around it.
Yeah, although obviously you do need a decent sized telescope to see it.
Yeah.
But yeah, amazing.
And then we've got this NGC 4697 Caldwell 52, which is an elliptical galaxy between 40 and 50 million light years away. It's a member of another group of galaxies, but this group is roughly about 55 million light years away. So it's part of one of the many groups in Virgo of all these clusters of galaxies. So it's quite fun to see.
Can I just say something about the Caldwell catalogue?
Yes.
Just in case our viewers don't know, the person who put the Caldwell catalogue together was Patrick Moore, because that was his middle name, Caldwell.
Yes.
He created his own catalogue of galaxies. So I just thought I'd let you know in case you didn't know.
Yes. Thank you for that. And there are quite a few which I've got labelled as 5 different meteor showers, which have a radiant point from various points of this constellation. So they vary from February with the Pi Virginids, going right through March and April. So there are some quite interesting ones. Obviously, the ZHR rates will be quite low, and they won't be very bright at all. But obviously, having that many meteor showers from the second largest constellation in the night sky is quite interesting.
Yeah, that's interesting.
Gosh. And then we've also got Quasar 3C273, which was the first ever quasar to be identified. And it's at a magnitude of 12.9, so it's well within the reach of us astrophotographers to capture. And it's
can you see Virgo from where you are? Yes, you can.
Yeah.
Yeah, you ought to have a go.
Absolutely. And it's approximately a distance of 2.4 billion light years away. And the central supermassive black hole is roughly 900 million times the mass of the sun.
Wow. Now that is a truly supermassive black hole.
Absolutely. That is quite a big beastie. So should be quite a thing to do. So might be worth an interest of getting some of these objects again during the spring period to get all these objects in and see how that goes.
Yeah, absolutely.
So that covers all the major things about the constellation of Virgo.
Thanks very much, Roger. Really interesting. Thanks for doing the constellation of the week. Yeah, interesting constellation. Well, they're all interesting in their own way, of course, but there are very, very few boring constellations. So
I let Michael do the little ones and I do the big ones.
yeah, that figures. Yeah. So,
I haven't got time to do the big ones.
yeah. Ian says, "Love the snappy names." Yeah, they're really snappy, aren't they? So, so there we are.
93C273.
It rolls off the tongue.
It does, absolutely. So anyway, moving on, it's that time when we, as space travelers, we step outside the capsule, remove our space helmets, and breathe in the hard vacuum of human stupidity, which is what we're going to do now with Einstein of the Week.
Hey.
And here we go. So this is when we delve into just quite unbelievable things that people say about the universe on social media. Haven't got many this week, only got 4 this week. But anyway, let's have a look and see what we've got for Einstein of the Week. The first one is called it Facebook Science. This has been going around many science pages on social media.
Definitely.
I just thought I'd warn you about this. You probably know. But anyway, just in case. It says the whole world will go dark for 6 minutes on August the 2nd in a solar eclipse that happens once in a century.
Actually, the number of times I've had that sent to me.
I know.
Yeah.
I know. Well, firstly, the solar eclipse on August the 2nd is August the 2nd, 2027.
Yeah.
Visible from North Africa, southern Spain, and so on. In a solar eclipse, the whole world doesn't go dark. Only the bit that's in the shadow of the moon goes dark.
Yeah.
But this has been doing the rounds, and looking on social media, it's unbelievable how many people are seriously believing this.
Yeah.
So just a warning if you come across this.
That's this Saturday, so let us know.
Well, absolutely. If you do see this,
I think. Sorry, what I was just going to say. I think the why this is going around. If you look in the bottom left-hand corner, I think that's why they put it out there.
Yeah, absolutely.
Send a gift.
Yeah.
I wonder if Vegas has odds about whether this will happen or not. I mean, this we could rake in some serious money.
we could.
Yeah.
But do you know one I haven't seen doing the rounds as much the last couple of years is the infamous in August Mars will be as big as the full moon in the sky.
Yeah.
All right.
I was only thinking of that the other day.
Yeah, it's gone around every August for at least the last 15 years, to my knowledge. But last year I didn't see it so much, and I think I know why that is. It's because it was going around via email, and now, of course, nobody's really using email for that. They're using social media instead.
Yeah.
So that may be the reason. But no, Mars will never ever be as big as the full moon in the sky. That goes without saying. Anyway, so if you do see this on social media, just do us a favor, put a comment saying you're talking bollocks or something like that.
Yeah.
Because, as I said, lots of people seem to be believing this. So there we are. All right, moving on. Number 4. That was coming. Number 3, Satanic Saturn. Okay, guys, first of all, identify the image.
Well, clearly, see, would that be Iapetus in front of Titan?
Not Iapetus.
Is it Mimas?
Is it what, sorry?
Mimas?
No.
Is it the moon?
Enceladus.
No, not Enceladus. I'm going to have to tell you.
Grapes.
It's Rhea.
Oh.
Really?
Yeah. So this is, as you correctly said, Titan, quite obviously. A lovely Cassini image of Rhea in front of it. I really miss Cassini because of its ability to come up with stunning images like this. Really miss Cassini. I'm sure I'm not alone in that. Somebody on social media didn't like it. And they said N Jehovah, not for you, 666 demon emoji and United States flag.
And what does that mean?
Pretty clear what that means, I think.
Well, I don't know, but it sounds horrible. The 666 being the number of the beast and the demon.
Yeah.
Not for you, devil, USA. I think that
Yeah,
means.
that's right. Something like that.
Yes, Diablo, isn't it? So 666 and the
Yeah.
devil.
I'm
just looking at the name as well.
I did reply to this person.
No.
Yeah, I did. I had to. I basically said, "Are you serious?" And he just replied, "We'd go to hell." So, there we are. Which I can't do, of course, because hell doesn't exist, as we know. But anyway, he probably doesn't think that. But there we are, Satanic Saturn. So make of that what you will. Number 2 is actually Einstein moment of the week. Now, I have to say, first of all, I'm all in favor of people coming up with their own theories about the universe. And, that's how things start, with people having an idea about the universe, about any aspect of the universe. And, there are countless millions of armchair scientists obviously out there thinking that they've come up with solutions to some of the universe's biggest problems. So I'm not criticizing the guy who posted this, but it just made me laugh. And let me show you why. He said, "I legitimately have a hypothesis for what dark energy is, not a joke at all, and I really need to talk to a research person at NASA Universe." Again, not a joke. This is the bit that made me laugh. "I have equations and everything. I also may know what dark matter is as a result. I really had an Einstein moment," hence Einstein moment of the week, "and I'm looking for the right ear." So that just made me giggle. I have equations and everything. So
thank goodness for the uneducated, for they shall keep us happy and entertained.
Yeah.
Did you reply to that one?
No, I didn't. Because the guy, at least the guy's thinking about things. He's trying to work things out, which is great. But I do feel sorry for him because he's got equations.
What if he's right?
Yeah, I know.
You never know.
But, you never know. But he's got equations and everything. So
why doesn't he write a paper? And then we'll all have a look.
Exactly.
All have a laugh. Right?
Yeah. Okay. So that's number 2, and lastly, number 1. Right. Identify the image first of all.
Shoemaker Levy.
Shoemaker Levy. Yeah.
Yeah. These are the giant scars that Comet Shoemaker Levy, or parts of Comet Shoemaker Levy, made in the atmosphere of Jupiter. And one comment on social media about this. So mankind has left its footprint on another world after all.
Oh, right.
Yeah. Which is why I entitled this one, "Read the article." Because, clearly this has nothing to do with humans. So this left me perplexed, I tell you.
What's interesting about that is that the Galileo mission did send a probe hurtling into the atmosphere of Jupiter.
Yes.
That's true.
There were some bets going on, viewing it spectroscopically, not imaging, but spectroscopically, as to whether it would dig up water. It did not in the spray. But in a broad sense, I suppose, it could have made a mark, like one of the Shoemaker Levy's comments.
I don't know. It's probably traveling far too slowly to do that. I mean, it was on a parachute, wasn't it? So.
Right, but the point is, we have sent something into the atmosphere of Jupiter, and it seems like maybe the sky's getting things like that kind of confused.
Yeah, maybe, and also, of course, Saturn with Cassini.
Yeah,
same thing.
Right, with the mission at the end, yes, the grand finale, right,
and also coming up Juno as well into Jupiter.
Yes.
Yeah. So we are actually leaving our marks on other worlds. So there you are. Anyway, that's another tour through the inanities of social media for you. And
interesting.
yeah, so there we are. Hope you enjoyed that. And Ian says, I really want to know the equations now. Yeah, because you know he's got equations and everything. I don't know what the everything is.
Yeah.
But there we are.
Yeah.
So there we are. Einstein of the week for you. So that, I think, just about brings us to the end of this evening. Apart,
I don't think so.
I hadn't finished.
Oh, okay.
Because to finish tonight, we're going to go over to Daz, and Daz is going to be talking to us about predicting events like the Carrington event. So Daz will tell you all about that, I'm sure.
Yeah. There you go.
So
can you see that?
Yeah, we can see that.
Right. Okay. Let me just go over here. Just get this up. Right then. Now, this is the reason I've sort of brought this up is that basically, the other week when we'd finished the show, we were just sat around chatting like we normally do, and somebody, Tom, posited a question as whether or not last year we had two quite big aurora events, one in May and one in October, and he asked me which did I think was the strongest, which was the biggest. And basically, I hesitated to answer because, I mean, it all depends. What do you mean by biggest and largest? And this, so I suddenly thought, well, the best thing to do is describe how, basically, predicting a Carrington type event is not easy. And the reason we use the Carrington event, this is used as sort of like the benchmark of all large solar storms or geometric storms that hit Earth, because it's been classified as one of the biggest that we've actually ever seen. So let's get into this a little bit. So yeah, so basically what we're saying is predicting a Carrington type events is not easy. So what we'll do is we'll just move on. So what was this actually when was this actually happening? Well, the actual observation of the Carrington event happened on the 1st of September 1859. So we're talking about in Victorian times. So we've got to set basically what the limitations there were for the Victorian astronomers. I mean, one, they didn't have any space assets. They did have ground-based telescopes, but telescopes had only been around 100 years or so. Observations are basically in optical light and through basically the window of the atmosphere, because that's what they were looking through. They had no sensitive cameras so they could image these things, what they were seeing. And basically they had no flash filters to show in the sun in different wavelengths, which gives you different perspectives on what's happening on the sun. But the best way they used to do is they used to project the image of the sun through a small hole onto a piece of card, and then what they used to do is sketch the sunspots that they could actually see. And this is what was going on this day. But also they had zero knowledge of the workings of the sun. I mean, in Victorian times, there some people thought the sun was just a huge piece of coal burning. They had no, they basically they just didn't know, and they had no idea that space weather actually existed and how it affected us on Earth. So basically, we're talking about Christopher Richard Carrington. He was observing a large collection of sunspots, and he was drawing them. And he was using a 115 millimeter refractor telescope. At the same time, somewhere completely different, another chap called Richard Hodgson, using a 4-inch telescope, was actually watching the same sunspots at the same time. This is the sunspot region Mr. Carrington was looking at. And all of a sudden, what both he and Hodgson observed was what we call a white flare. So basically, this sunspot region here actually flared, and they actually saw it with the naked eye. And it's the first time that anything like this had been observed. Now, in this drawing, you can see two worm-like objects. I think, can you see my cursor where I'm? But there's these two worm-like objects in the center of here. Now these are actually reconnection points where where the flare's gone off, and the magnetic fields are reconnecting. They're called magnetic arcades, and he was able to draw these because they lasted for quite a few minutes, you know, sort of 10-15 minutes. So he was able to draw them, and basically it moved from point A to point B. So this is what he drew. So it was the first time like this had ever been seen. But unbeknown to them, there was also associated with a solar, with a CME, a coronal mass ejection, and that's where huge uh, prominences break away from the sun because of the flare, because the flare is pushed out. This a violent act, and it pushes out tons and tons and tons, hundreds and tons of thousands of tons of material from the sun out into the interplanetary medium. They do become an ICME then, but we're not going to go into that. So I'm not going to go into the detail of what they are. If you want to know any more details on the mechanisms that I'm talking about, just go to our on YouTube and look for our site, Space Oddities Live, and look for our selection on astronomical space bytes, space bytes. And then you'll find them all there. And we're adding to it all the time, so you'll be able to understand more of what's actually going on the sun and what's causing this. So we'd had the flare in the coronal mass ejection, but of course they didn't know anything about that. But what also was of interest is about 8 minutes later, them actually, well, just about at the same time as this was going on, when they actually saw the flare, which is 8 minutes after the thing, there was this magnetometer in Kew Gardens actually traced the magnetic storm hitting us, because when you get solar flares, they produce X-rays. And this is what's hitting us. And if you can see my cursor, I hope you can. The first blip on the lower counter, you can see a nice little blip there. That is called a magnetic crochet. That is the actual start of the actual storm. But also these flares, they produce radiation storms, or SEPs as we call them, solar energetic particles, so the actual X-rays are traveling just at the speed of light. But the radiation storm will appear and hit the Earth about an hour or maybe a little bit longer afterwards. And this is where, if you look, it climbs up, both traces start to climb up, and that's the storm actually hitting. But of course, they weren't aware of all this going on at the time. But they basically got together, it's one of their sort of astronomical things, and they started to realize. And then, of course, then what happened was, 17 hours later, the actual main solar storm arrived. Now, these storms usually take 3 to 5 days, but they didn't know all of this. But so the solar storms tend to travel very slow. So the flare travels very, very fast. The solar storm very slow, and they usually take 3 to 5 days. But this arrived within 17 hours, and this is when we had all the auroras and the everything that happened beyond it. So how has the 1859 event affected many views of Carrington time events? Now, also with in 1859, and the reason that this is the most investigated flare, geometric storm, is because the basically what I've forgotten what it's called now. Basically the you had what was the sort of at the time the internet of the time, and that was the communication system that they were using. And I've lost the telegraph system. Sorry, the telegraph system. And of course, you remember all the dot dot dots dash 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 dash, and they'd print out things like that. Well, what happened was, is when the main storm hit, currents were induced in the ground, and they had to escape somewhere. Well, miles, hundreds and hundreds of miles of telegraph cables had been laid. And what was happening? The current was being induced and conducted into these cables. And what happened was, is the instruments at the stations started to chat away and do all these different things. They even started to spark. They used ticker tape, and the ticker tape in some places actually caught fire. They disconnected because all these were run on batteries. Remember, there was no mains system, no power system set up. So they disconnected the batteries, but they were still able to communicate with the stations because of the power that was induced into the cables. And we won't go into that, but that's what was happening, and this is why it made the headlines. And then, of course, we had the huge auroras, which were seen literally almost all over the globe, which made people suddenly think, well, what's going on here? Well, of course, sorry.
Did the slide mean to move on at that point or not?
No, I'm just going to start it now. So,
okay, just writing in case.
Doing a bit of filling in. So it says, both in the press and online, we find these events described in doom and gloom. So this is because things burst into fire and things that have happened since, we tend to get, when we know that there's a big storm coming, we get all these headlines, which are Carrington-like events are mega flares, kill shots, or micronova. Armageddon from the sun, or the wrath of God. Paragrid killers. Basically, any space weather event that will spell doomsday for the Earth's weakening magnetic field and to all the electronics on Earth. Electronics will burst into flames and buildings will burn down. A Carrington event will kick us back into the Dark Ages, and the radiation will be lethal to all on Earth. So we get all these doomsday things that, what we call clickbait these days. But this has been going on for decades now. Every time we think there's going to be some sort of big geometric storm, you get all these doomsday scenarios, and basically rubbish. This is Hollywood fodder, the next big blockbuster. We have experienced far more Carrington events than you probably realise, but we're still here. But we've survived. Since the Carrington event, there's been at least 30-ish events that could be classified as Carrington type events. But again, as we said, it's very hard to classify what sort of how do we classify a Carrington event. So first of all, we've got to look about what type of events actually happen on the sun, which will give us these geomagnetic storms. So first of all, we've got solar flares. Now, again, as I said, these happen where you've got large sunspot regions, the magnetism is being all wound up and all that, and suddenly everything will give way, and you get this whole expulsion of, as I said, they produce X-rays. They travel very, very fast. When they hit Earth, they will produce radio. They produce radio bursts, so they will actually interfere and cause radio blackouts on Earth. And then they will be followed by a radiation storm or a SEP storm, solar energetic particle storm, which are mainly protons and electrons. So as I said, and also that will also travel very, very fast itself. And then so we've got that event happening, and of course most of the time we'll notice that these are going on, is because we'll get the radio blackouts on Earth, the two-way radio communications. The stronger the actual flare is, the higher the wavelength it will interfere with. So it starts with the long wave, then it'll go to medium wave, and so on. So that's what we're looking for when we see these coronal mass ejections. Now, as I said, these are the where you get lots of material expelled out into space in a violent action. And again, these are actually they are massive amounts of solar plasma and enhanced magnetic fields, and the plasma is held in place and it expands like a bubble by the magnetic flux rope that forms within this, and it will expand out into space. And because it's expanding and you've got all this material, it's being pushed along, and you'll get strong shock waves actually out in space, and they can be measured. But they travel slower usually around 15,000 kilometers a second. Now that's slow, isn't it? So anything that gets, once you start getting higher figures than that, you know you've got something seriously coming at you. They usually travel to Earth between 2 and 5 days. And these will actually, if they're big enough, will actually cause us a magnetic storm, which will give us some interesting effects, but also massive aurora. Again, if certain ducks fall in line, there's a lot more involved in it. And as I said, if you go and look at our space bites, then you will actually see these explained in a bit more detail. And also the people who've been with us for a long time will also know about the space slinky as regards coronal mass ejections and things like that. How the actual bubble that's coming out is driven. You've got a huge electroflux rope, and that's what in containing all the plasma and the radiation or the seps inside it, and it travels out and hits us, and that's when we get the fun and games. We've also got coronal holes. Now, these you can only see these in certain wavelengths, but when you see them, as you can see, they look like big holes in the surface of the sun. Well, they're not actually, they're just areas where there's very little magnetic activity going on. So all the yellow is where all the electromagnetism is actually going on. And what happens is because there's no action going on there, it means that this radiation and the lights and everything else can escape from those areas, and that basically enhances the solar wind towards us. So they will make the wind speeds faster, and they alone can actually cause auroras, but more up towards the Arctic and Antarctic Circle. And last but not least, you've then got these SEP storms, which I've been on about. Now these can come from, we've been sort of like swathed with these all the time because they are emanated from the sun all the time. But sometimes we can get things called sort of like flares or even more CMEs that actually come off the face of the sun. But because they're on the face of the sun, we don't detect them, and then we'll also be then all of a sudden we'll be hit by this radiation storm that we didn't even know was coming our way. So these are the four sort of like types of events we should be looking at. Right. So solar flares produce X-rays and solar energetic particles, or SEPs, which is also known as a radiation storm. The X-rays travel at the speed of light and arrive at Earth in 8 minutes, while the SEPs arrive a little time after, causing the radio blackouts. And then, as I said, these radio blackouts can last sort of like just a few minutes, or they can last a couple of hours. And it's interesting to see, if you look on the NOAA site, they've actually got an animation. And if you know one has gone off, you can go back, look at the animation, see how it actually destroys the radio sort of like traffic in that area. Coronal mass ejections, they expel millions of tons of sun's material and plasmas trapped within a magnetic shield, which is also expelled out into the interplanetary medium. Usually takes around 2 to 5 days to reach Earth, but can cause large magnetic storms. And coronal holes, these can produce extremely fast solar winds and again radiation particles. Coronal holes have also can enhance how fast the time is of these CMEs and these and the radiation storms from the flares, how quickly they travel to Earth. Right. Anything arriving in less than 24 hours is considered a Carrington type event. Fastest travel between the sun and the Earth, remember that's 1 astronomical unit, at the moment is 14.6 hours in 1972. Now, what I hope to be doing next week is I'll be doing, we're going to select from these 30 odd solar storms, and I'm going to tell you about them and how they affected the Earth next week. So There we go. When the geometric storms arrive at us, we measure them with a G number, G1 to G5, and they start from minor to extreme. And you can read there basically what they actually do. Minor, weak power grid fluctuations, minor impacts, migratory birds are affected. Aurora is commonly visible at high latitudes, which, as I said, is up by the poles. Moderate transformer damage, G2. Corrective actions to space orientation may be required. Aurora may be seen, and this is the NOAA site, so most of these are using American locations. And then you got strong, which is power system voltage corrections, blah blah blah. Then you got severe, widespread voltage control problems on power grids, HF radio sporadic, satellite navigation, and these. And then you go up to the 5. Once you get to 5, we stop there, because anything bigger than a 5, we're going to really know about it. So that's how we actually measure the actual radiation storm when it actually hits us. So this is a map showing the northern hemisphere. I've got 2 here, because one's showing America and the other's showing sort of like Europe and the rest of the world. And then you've got the southern hemisphere. And this is basically where you expect G1 is the green line. That's as far as you expect Aurora to come down to, but it will expand beyond there, because you're talking about G1 plus. Then you got G2s, G3s, and so on. And if you look when you get to the G5, you've covered most of Northern America and quite a lot of Europe. But once we get in, you can also see a KP number there. That is how we measure the magnetic interference within our own magnetic sort of like system around the Earth and stuff like that, and how it's affected us. It will go up to KP9, then after that it stops, but it doesn't mean that storm was a KP9 and that's it, because the 1859 storm has been re-engineered. They've taken it back to they think it was the actual storm itself was the flare itself was an X43, which means the KP index would have gone absolutely manic. So as you can see, but when you look at this, when you go on KP9, you can go all the way down into the Mediterranean, and you will see Aurora. Now I'm talking about with eye. As I said, the Victorians did not have cameras like we've got the sensitive digital cameras. Your phone will pick up Aurora a lot more than what your eyes will pick up. So if you're taking photographs of the sky just on the hope, you will see Aurora in the photograph. So of course that now means that we can extend it. I mean, we can also, I mean, some of the auroras that we're talking about would have been sort of like possibly seen actually from the equator. So this is what we're sort of things we're looking at. Now this is this here is the active sunspot region from 1972. Remember when I said we had that really fast traveling time? It was actually 14.6 hours that it took for this to arrive at Earth when this actually went on. But we'll talk about that, more of it next week. But so there we go. There are 5 quantifiable parameters in a solar storm. But rating Carrington events is not an easy task. Not one solar storm wins all the categories. So here we are. Now these are just images of coronal holes that were taken, and these were on 2 different. It's the same as coronal hole, but on different rotations, Carrington rotations as we call them. So measurable space weather effects. Sudden ionospheric disturbances. That's what happens when the storm actually hits our magnetic shield, our magnetosphere, which protects us. The biggest of that was the 4th of November 2003. So I think that's, if I remember right, that's probably one of the Halloween storms. So we've also got solar energetic particles. So we're looking at the radiation. Now, at the moment, it seems that August and September of 1859, so our Carrington event, actually takes the gold in that. Because as I said, they back-engineered these, knowing that what we know now. And mostly they've had to use the aurora and the magnetometers that were around at the time to be able to sort of like guess what was going on. But they think, to be honest, that all the values for these measurable effects have been underestimated for the Carrington event. Solar wind speed, again, as I said, that was August 1972. As I said, that was the horseshoe active region that we just saw. Magnetic storm, so that again, that comes down to telling us about the aurora and the effect that it actually has on the ground as well, because some of the radiation will get through, but literally 90% of the radiation will be deflected by our own magnetosphere, and we'll talk about that in a little bit as well. And then last but not least, aurora, how far they've been spread, and that seems to be something February 1872. Just want to get rid of something. There we go. The 4th of February 1872. That's when the was seen at the lowest latitudes, because remember, the aurora come from the top and the bottom of the Earth, North and South Pole, and then they spread down. And that was because I think actually I will just move on a bit. So what we're looking at here. So this is a drawing of the black hole the Carrington saw. So was the 1859 Carrington event the biggest and baddest solar storm recorded? The fastest? No. 1859 comes in at second at 17.6 hours, and I've got to reach Earth. Strongest flare? Maybe. Looking at what all the evidence that we can gather from what we know now, it has been calculated to be possibly draw with the 2003 Halloween storms. Biggest radiation storm? Maybe, due to the extensive aurora. You only get that if you've got a lot of radiation coming in through the poles from there. Aurora, silver again, because the latitude that it came down, it was seen visually. Remember, this is visual, not with any cameras or anything, at 20 degrees north. But in 1872, it's been reported that it was seen down as low as 19 degrees north. So not gold medal every time, but it's placed, the 1859 is placed on the podium in all of them. So this is why it's been set as the benchmark that we're going to actually look at. So now this image here, and I was talking about last year, this is one of the images that was produced by somebody to show the October 2024 solar storm that hit us. It's well exaggerated, as you can well see. I mean, we don't get prominences and flares coming out that far. If we did, we'd be in serious trouble. So all of that being said, the next question is, will the next Carrington type of event be the end of the civilization as the tabloids and the scaremongers predict? We have lived through loads of Carrington-like geomagnetic storms. Sorry. Each one was different. As I said, I've counted up to 30, but we are still here. We've survived. The large storms will rain on our parade for a few days. Of course they will, or even weeks. But that all depends upon what the storm's made up of, what its constitutional parts are. And there could be consequences like radio blackouts affecting emergency services and transport. Power networks could collapse, creating widespread power outages. Damage to satellites, no cell phone communications. Oh, can you imagine that for the kids? Even worse, internet outages. God, they'd have to talk to people. Crashing all industrial and domestic systems, and also military systems as well. I forgot to add that in there. GPS anomalies, grounding all drones and affecting any devices using GPS location. And again, if you look at all these just alone that I've just put up now, these will all again affect emergency services, especially where if there's been some major catastrophe somewhere in the world, and you've got people actually trying to save people and rescue people. They got no way of getting drones up. They got no way of communicating. So to actually be able to manage where you're actually running a emergency service, a big intervention, would be virtually impossible. So we've got to basically try and mitigate these against these things. Medical devices like pacemakers could be affected. And again, when I'm talking about this, this is more a case of, especially if you're flying at the time. Now, where I said at the top about radio blackouts and all these other things, when we do get big storms, the like the CAA here and the FAA in America will put out warnings to all flying to all planes not to fly, or set out a warning to basically say don't fly over the poles, because of course this is where all this radiation and all these energetic particles are coming in, and you will get a bigger dose of radiation than you would if you were normally flying. So they would tell basically everybody, stay away from flying over the North and South Pole, which a lot of flights do. They go up into the Arctic Circle just to get to America from Europe and things like that. So they have to then move themselves south just to to avoid all this extra radiation. And pacemakers, they could interfere with, because the pacemakers usually sort of like set to actually work at a certain pace, and if that's disrupted, then they have to be they have to be corrected again, and that can only be done by using computers. And of course, if you haven't got the access to them, then I think, as we also said, LEO satellite deorbiting. Due to extra drag created by the Earth's atmosphere expanding. Of course, we can remember 2019 when we had a flare, and they sent up a load of SpaceX Starlink satellites, and 40 of them failed to make orbit because the atmosphere had expanded and the drag was too big for them to be able to achieve orbit. So they all returned to Earth. Well, more and more of these can actually happen as the atmosphere, because because like I said, basically it means the satellite is traveling through more of our atmosphere, causing more drag and slowing it down. And unless it can correct itself, it's going to come down. And we've got to talk about astronaut safety, increased radiation exposure to astronauts and space tourists, because we're getting all these tourists and all that flying up there now, doing things. And of course, this also then, because like I said, we've got the International Space Station. Now they have a facility within the International Space Station where they can move when these when there is a solar storm coming. They can move into this area, and basically they're surrounded by water tanks, and that will protect them from excessive exposure. But of course, if you're talking about flying to Mars and places like that, then this has got to be really thought about, and some way of mitigating this this exposure. So, can we mitigate these extreme weather events? Yes, we can, but only to a certain extent. Space weather is like weather, Earth weather, and needs to be treated in the same way. Space weather needs to be studied to enable us to be able to predict these big geometric storms, and thus instigate protective measures. And one day, maybe the space weather will be part of the daily weather forecast. Now, this is beginning to be taken really seriously now, especially with all these satellite people like SpaceX and things like that. They are always in contact and looking at indications that there's going to be a solar storm going on, so that basically they can either power down the satellites, or they can introduce systems which will actually protect them when these solar storms actually hit them, and so not damage them. So it is really important that we need to know these things. It's the same with electricity grids. They need to, I mean, because we had the, when was it, 2009? No, not 2019. When was it, 2009 or something? The Quebec incident where the solar storm crashed the Quebec Kingdom. Basically, again, we had this problem like we did with the telegraph, where in the cables, the induction of the new current increased it, and basically it started melting the transformers because they had oil in them. So they overheated, the oil boiled, and these transformers melted. Well, now they're moving, because they've learned their lesson. They're moving over to dry transformers where this can't happen, and also they're putting in more trip devices so they can control where the electricity is going. Now, saying that you just want to put a trip switch in there is not the right way to go, because in fact what they need to do is basically turn off the trip switch, so that it can't actually trip itself. Because if a trip goes off, that means that electricity that's been induced into the cable will go to somewhere else. And if you've got things tripping off to save the transformers on that line, they're going into another line, and that means they're going into fewer transformers. And so you've got to have the reverse effect. There are ways of doing it. We've survived them so far. The big storms we've had so far, yes, there's been some problems. And again, like I said, with the satellites, just recently in May last year, we had downlinks from the downlink from Starlink affected. They had more complaints that people were not getting the system that they were expecting. So yeah, this is what we've got to do. But as I said, no two storms are exactly the same. So to actually say which ones are going to cause the most damage and be basically more disruptive to us is almost impossible. But we're getting better at it. We've got all our assets in space now. We've got the satellites out there which are measuring between us and the sun. We've got things actually orbiting the sun, and we've got the Parker Solar Probe actually flying through the sun's atmosphere on huge orbits. So we're getting stuff there. We're gaining more and more knowledge. And the more we know, the more chance we've got to predict it. But remember, if it's a big flare, we've only got 8 minutes to act. So, like I said, we need these things. I think with the systems that are between us and Earth, usually at Lagrange point 1, they give us quite a bit of notice, but you've got to act really quick to protect yourselves. So, as I said, to actually predict what is going to be a Carrington type event is very, very hard. And I'll just give you one where basically we had a near miss. In 23rd of July 2012, an ultra fast CME directed away from Earth, luckily for us. In fact, it was just beyond the western limb. It had rotated out of off the face of the sun, erupted, and we could see the eruption from the side. Now, this was, as I said, it was ultra fast, but it was heading directly towards Mars. But it was such a big one that it actually created what we called a 360-degree halo, which means it actually shook the sun so violently that literally matter and radiation and everything else was shaken off of the surface of the sun, creating sort of like a huge sphere of a magnetic storm, radiation storm moving outwards. And we were going to be hit by this. Now, as I said, this CME was directed towards Mars. So that was getting the full force of it, and it was traveling really fast because that's where the event went, and boom, it's coming right straight for you. But we were going to get a side swipe from this because we were, sort of like about just over 90 degrees off. But it was going to hit him. Now, to tell you how fast this thing was moving, and when you think about how close Earth is in 1 astronomical unit, and where Mars is, the actual storms hit Mars and the Earth at the same time. So when it was moving towards the portion of the storm that was heading towards Mars was traveling so fast that it hit, and towards us it was slower, but they still hit at exactly the same time. That shows how fast it was. But because it was seen and it was monitored and it was estimated, NOAA was able to safe the rovers. Basically, that means sort of like switch all the systems, most of the systems off, send them basically to sleep until the storm had passed over. But they still measured what actually passed over these robots as well. Things like Curiosity, I think it was at the time. or was it opportunity? I don't know which one it was. But yeah, so they had to, but they were able to, because we know what we know, they were able to save the rovers from actually being destroyed by a magnetic storm traveling towards them from the sun. So I'm going to leave it there. As again, as I said, if you want to know more details, go and have a look at our videos on YouTube, and look at our Space Bite ones, and you will be able to learn more and more about how the sun works, things like that. We're always adding to it, so the more that we know, the safer. So basically, don't be taken in by the hype. We've lived through tons of Carrington type events before, and we're going to carry on to live through these things. So, but to actually tell you how a Carrington event is going to hit us and what it's going to do is almost impossible at this moment in time. So I'm going to leave it there. And thank you very much, everybody.
Okay, thank you, Daz. Interesting stuff. And, you know, as we always say, we all take the sun a bit for granted, but just a reminder that, you know, these events do happen. They are extremely dangerous, and they could have widespreading and deep effects on our technology.
I'm sorry if I waffled there. I did tell people to warn me.
I did.
Oh, I missed it. Oh, of course, because I was looking at the PowerPoint. I didn't say. So I do apologise.
You see,
I do apologise. Sorry, everybody's missing their Horlicks. I do.
don't worry. Well,
But as I said,
Daz will be back next week, no doubt, with another marathon waffle. That could be a good snack, actually. Marathon waffle, or Snickers waffle. Anyway, we're going to draw things to a close now. So thank you to everybody here for their contributions. Thanks, Lou. Thanks, Roger. Thanks, Daz. And Michael, thank you for being here, even if it was just a short length of time. And we will see you next week. Don't forget, join the Patreon community. There you can keep up to date with what we have got coming up on Space Odysseys. And you can get some goodies for yourself as well as all the material that we present here on Tuesdays, and a lot of our videos as well, which we're slowly adding to. So do join our Patreon community. It's a lot of fun, and you will be supporting Space Odysseys and helping us to stay on the air, as it were. So Mike Beer says, really interesting. Thanks. Didn't seem like waffle at all. How much did you pay him, Daz? So there we are. If it's back to the 70s, indeed. And there we are. So we'd like to thank you all very much for being here this evening and for sharing this stuff with us. Not quite sure what we've got coming up next week, but don't forget it's Mars month in September, and we're going to have Nicholas Booth as our guest on September the 2nd to talk about his work as a science writer and his books, including The Search for Life on Mars, which is why we particularly want to speak to him, of course, as it's Mars month. So put that in your calendars. Everything's on Patreon. Don't forget the website. If you want to submit an image to our gallery, then please email it to gallery@spaceodysseys.space. And thank you very much. So from myself and Daz, from Lou, from Roger, and from Michael, have a fantastic week. Take care of each other. And we hope you enjoyed the show. And don't forget to like, subscribe, and comment. And the commenting is quite important. So when we finished here on YouTube, in the comments on YouTube for the video, just please put something, anything will do, because the YouTube algorithm looks at the number of comments when trying to make a decision about whether to promote our videos to other people. So comments are a very important part of that, as are the views, of course. Thank you so much. And from all of us at Space Odysseys, have a great week. We'll see you next week. Bye-bye.